Hello. I think you should hear me and see the desktop now.
We
You're
can.
good.
Great.
Yes.
Thank you. Okay, now I need to get the chat window up and okay, we're going to pick up where we left off last week, playing around with showing we're showing what we can see externally about process states and system calls. What we can do by running programs and using Task Manager to see a little bit about process states and see a little bit about system calls. We haven't started this stuff on system calls. We'll finish the stuff on process states today. I think we can, and maybe do the stuff on system calls too. Okay, so I'm going to download these two folders. Oops, I forgot to fix that. Oh, it's remember, it's up there. Get the folder view, and it's in the folder for class, and there it is. Okay. Okay. Remember, in terms of process states, we're kind of trying to see this picture here, and the other was no, not that one. The picture in the book on states. I had a link to it. Was it this one? Yeah, there it is. Okay, that picture there. Yeah, this picture here, which shows the idea of the CPU running this process or this process, and merge that with this picture here, meaning one process is either in the ready or block state, and the other process is in the running state. So one of the processes is in the running state. That's the one that the CPU is currently pointing into. The one that has this program counter pointing into its process. Okay, that one would be the running state. The other one, like this one here, would be a ready state if it wasn't waiting for I/O. If it's waiting for I/O, then it would be in the block state until the I/O it's requested is ready. Okay, and remember the sequence was, if a process is ready and it's made running, that's a context switch. And the way you do that is that one of them is running. You're going to stop running that one, start running this one. So the one you're going to switch from, you take all its CPU registers and put them in its process control block. Remember, the process control block is a mirror image of the CPU registers. So when the timer interrupt fires and it's time to switch from him to him, the timer interrupt fires, you enter the operating system. The operating system starts the process of copying all these registers into the process control block. Then it copies all, then it chooses who to run. That's the next chapter, the scheduler. Choose who to run next. Copy its process control block, which was put there the last time it was ended running. Put its process control block in the CPU. That puts the CPU down in here, and now that one's running. And remember, that involved switching from user mode to kernel mode back to user mode. This guy was running in user mode. The timer interrupt fired, forcing the CPU into kernel mode up here. The operating system does the context switching, and when it finishes the context switch and it puts this guy's process control block into the CPU, the last thing that happens is the CPU switches back from kernel mode to user mode to go enter in here. Okay, so that would be a transition from ready to running. Okay, now this process is running and it needs an I/O operation. It does, I show it up here, it does a system call. The system call enters into the operating system. The system call is a software interrupt as opposed to a hardware interrupt. It does the same thing the hardware interrupts do. When you make a system call that puts a specific address into the program counter, it, as we say, traps you into the operating system where the entry point is for that system call. So calling open file actually traps you into the NT, in the case of Windows, the NT open file system call. You transition from user mode to kernel mode. Okay. You're running this code in here in the kernel, and the operating system notices that, hey, this is going to take a long time. You've asked me to open a file. I have to communicate with the hard drive. The hard drive takes a long time to spin up and to move the heads. So the operating system decides that since this is going to take a long time, it's going to put the process that made the request, it's going to put that process in the block state. It's going to take so long for it for this system call to take place. So the process that was running is put in the block state. Okay. So whoever made the system call gets put in the block state. That means its CPU registers are put into the program, its process control block, and it's put into this queue of block state, of block processes. Since the CPU is not running that process anymore, it makes this context switch to some other process that was in the ready state. Okay, so if what process got put here, then the operating system went over, after it put this guy in here, it picks somebody from in here and puts them running. Okay, now there's more to the story. The process that got blocked, its work is being done by the hard drive. At some point, the hard drive is finished with its work, and it signals the CPU that it's completed a task. When you signal the CPU, you jump away from whatever process you're running into the operating system. So the operating system now is actually doing work for this process while it interrupts this process, because this is the one that did the system call. This is the one that's blocked, waiting for the IO. When the IO is done, the hard drive signals the CPU. The CPU takes this, the CPU is taken away from the currently running process, jumps into the operating system, into the hard drive device driver. The hard drive device driver lets the operating system know that that a task has been completed. The operating system knows the task belonged to this process, and the operating system knows that that process now can move from blocked to ready because the task it was waiting for has been completed. Okay. Now that all happens while some other process is running. See, that happened while this process was running. While some process was running, the process down here in block state was what it was waiting for was finished. The operating system knows that because the device that was finishing the work signals the CPU. That traps the CPU into the device driver in the operating system. The operating system is updated about this task being done. The operating system realizes it was for which particular process, and it moves that process from blocked to ready. Then it goes back to running this guy. You know, the diversion of the operating system to move this guy here to here was done while this guy's really in the run state. But notice he's not running at that point. For a little while, he's actually paused. The one that was running is actually paused while the CPU handles an interrupt from the hard drive. That's why it's called interrupt. It interrupts the flow of what the CPU is doing. The CPU is actually running this process in user mode. Some interrupt occurs, which puts you in the operating system kernel mode. The operating system handles the interrupt. In the process of handling the interrupt, it does some bookkeeping. It realizes that one process can move from blocked to ready. Then after it's handled the interrupt, done the bookkeeping, then it goes back to running this thing here. Okay. Then when the timer interrupt happens, the one that's running gets put back into the ready state, and the one that was unblocked could now get back to running and handle the data it requested. Okay. All right. So one of the things that your goal in this class is to combine these two pictures. Yeah. To be able to see how to combine the ideas in these two pictures of what's happening over here with what's happening over here. It should be a little movie that runs in your head that you can see, that you can think of the CPU as running program here, IO operation comes, CPU gets stolen over to here, CPU does an interrupt, handles an interrupt. Maybe it may not, the information from the hard drive may not be enough to complete the IO task. So the interrupt from the hard drive may update the IO operation, but it's not ready yet to be unblocked. But when the IO operation, when the interrupt is done handling, you go back to whoever you are running. At some point, this disk drive interrupts the CPU, and the CPU traps into the operating system and notices that the IO operation is completed. The operating system can move a blocked process into the ready queue, then go back to running this thing. Okay. The CPU is constantly transitioning between user mode and kernel mode. User mode when it's in one of these processes, kernel mode when it's in the operating system. It transitions from user mode to kernel mode either because of a hardware interrupt or because a running process makes a system call that diverts you into the kernel. The system call is your process asking the kernel to do something for it, so it's your process that diverts itself into the kernel. The interrupts you have no control over. If you're running here, like this could be a CPU bound process. It never makes any system call, but it can't somehow stop interrupts from happening. This thing is computing, but an interrupt happens. The CPU is taken away from it. The operating system does some bookkeeping, and then the CPU is given back to him. Okay, those are not called context switches. That's just a mode switch. If this guy's running and an interrupt comes in, you switch from user mode to kernel mode. The kernel does some bookkeeping maybe, and then switches back to him. That's a mode switch. You never left this guy's context. It remains him who's running. A context switch is when this operating system decides that this thing should change from running to blocked or running to ready. So when you switch from one process to another process, that involves a mode switch, but that's called a context switch. Okay. So a context switch is switching from one process to another process. A mode switch is switching from a process to the operating system. The mode switch involves changing user mode to kernel mode and kernel mode back to user mode. Okay. All right. So that's our outline of what we're doing. Okay. Now, we open. Okay. Yeah, I might as well unzip that one too. Now, all of what we were talking about. Okay, look. Now, here's a folder that has code that does CPU bound versus IO bound processes. So what that means is, in terms of these two pictures, CPU bound would be a process that once it's running, never makes an IO request and never makes a system call. So we refer to that as CPU bound. It's on the CPU and it stays on the CPU, and it never interrupts itself by doing a system call. Okay. On the other hand, another way to think about it over in this picture would be once the CPU is running inside this process, it never makes a system call. It just keeps running inside this process. Okay, so we call that CPU bound. IO bound is when a process is doing a sequence of IO operations, not just one IO operation. The idea is IO bound in this picture here would mean the process is running and it requests an IO operation, so it gets blocked. At some point, it gets unblocked and becomes ready. The IO operation was done. Then when its turn comes in here, it makes another IO operation right away. The idea would be that when we mean by an IO bound process is, as soon as it's running, it just requests the next piece of data. So then it gets blocked right away. Then when the data is ready, it comes unblocked. When it's turned to run the CPU it got one piece of data, now immediately requests the next piece of data. It turns out that in the real world of computing, processes act exactly these two ways. Any given process will transition between a phase of being in a compute bound phase where for a few seconds it just does nothing but calculations. And then after it's done a bunch of calculations, it'll enter an IO bound phase. Okay. So essentially what processes tend to do in the real world is act CPU bound for a long stretch of time, then act IO bound for a long stretch of time. So they do a calculation, then they store the data, they store the results and get more data. Storing the results and getting more data makes you IO bound. Then when you've got more data, you start crunching on it, and then you become CPU bound for a while. Then after you've done all the calculations, then it's time to store the results and get more data. And in the real world, you don't see processes doing a little bit of IO, a little bit of calculation, a little bit of IO. They don't kind of interweave them. They tend to kind of do a big batch of IO and a big batch of computing. So this idea of a purely CPU bound process and a purely IO bound process is kind of a natural way to study this idea. Okay, because from the CPU's point of view, from the scheduler's point of view, it's got some processes that are just doing nothing but calculations and some processes that are doing nothing but IO. And it turns out they're really the same processes. It's just that any given process, like a database server or a web server, tends to spend a little bit of time doing a lot of calculations. Then after it's done a sequence of calculations, then it does the sequence of IO. Usually we think of it as storing the results of the calculation and getting more data for the next calculation. Okay, so we model that usually with test programs. Like this program is a pure CPU bound program. Okay, and these batch files, I didn't write an IO bound program. I just wrote batch files that do IO. So each one of these is a little script file that like downloads something from the internet or copies a file to the hard drive over and over and over again to just keep doing IO operations. So instead of writing a C program that does a bunch of IO operations, it was easier for me to write them as little shell scripts. So like this one, it's one line. See, it's a lot easier to write one line shell script than to write 30 or 40 line C programs. That program calls wget, which fetches URLs off the internet. So you give wget a URL on the internet and it just downloads it for you. Wget's a real useful tool. It comes with Linux. It doesn't come with Windows. So I had to put a little copy of it here in this folder because if it was a Linux machine, wget would be there automatically. But on a Windows machine, it's not there automatically. So it was written for Linux. Well, it was written for Linux and Unix, but people have written versions of it for Windows. I can't remember if Microsoft keeps saying they're going to put a copy of it in Windows. I don't think they have. Let me just check. I don't think it's there. Okay. Now, there's another program that's very much like wget called curl. See, now curl is on Windows now. Recently, they put curl on Windows, and so I could have used curl instead of wget because curl is now part of Windows 10. And that was actually made recently that they made curl. It's called curl because it URL. I forget what the C stands for. It's something URL, and that's what wget does. Wget gets things off the web. Okay, so it was web get. So you give it a URL and it gets it for you off the web. Curl was I forget what the C, I think maybe it's copy URL, but people just call it curl. Okay, and it does pretty much the same thing that wget does. So I may rewrite these scripts to use curl instead of wget because probably all of you have Windows 10 by now, and curl is part of Windows 10 at this point. Okay. All right. So, but it's real easy to write these little, see, it just downloads a big file off the internet. That's like a one, I can't remember if I think it's a 1 GB file off the internet. Okay. Uh, this one gets a large text file. This is not a very large text file, but this guy's a famous artificial intelligence researcher, and he put a big text file on his website because a lot of AI programs need big text files to process. So but it's not really that big. It was big by the standards of a few years ago. It's only like about 6 megabytes. So you download that little file, that 6 MB file, but then you take the file you download is called big.txt. So you download big.txt. Then I wrote another script that says type prints out this file. That appends it to itself. That doubles the size of the file. Then it takes the new version, types it to the end of itself. Remember, this is the IO redirection that does append. That doubles the size again. So this is 6 megabytes. Now it's 12. Now it's 24. Now it's 48. Now it's 56. Yeah, and he ends up getting it up to a gigabyte. So if you run this file, it'll create a 1.5 gigabyte file. So you download the little file, and then this file exercises your hard drive. So it builds up a 1.5 gigabyte file of text on your hard drive by copying it over and over and over again. So that gets your hard drive really working. Okay, so this one exercises the hard drive. This one downloads off of the internet. So that's using your either your Ethernet connection or your Wi-Fi connection. And then this one downloads, oh, not that one. This one downloads that text file, the big text file, but it uses wget to download it. But instead of saving it to your hard drive, it prints it to your console window. So if you run this, right now it's doing two kinds of I/O. Well, see, that wasn't very long. It's modern. The internet's become so fast, but what that did was it downloaded it from the internet and printed it to my console all at once. So I'm doing I/O on the Wi-Fi connection, and I'm doing I/O on the console connection. And I need to find something much bigger than 6 megabytes for that. I need to find something that's fairly. I've been looking. I'd like to find somebody who has something like 100 megabyte text file on the internet, because things are fast enough now that a 5 megabyte, you see a 6 megabyte text file, it's all of 2 seconds, 3 seconds, 4 seconds worth of I/O operation. Okay, but yeah, I'm looking to see if somebody has got. I've been looking lately to see if I can find somebody for testing purposes who's put like a large text file up on a website so that you can download it just for testing purposes. These are binary files, so you don't want to print them to your console. Like when it downloads this 1 gigabyte file, you don't want to print that out to the console because it's a binary file, and it doesn't work very well to send a binary file to your console. So it really should be. It'd be nice to find somebody with a really large. I could put one up on my website, but I'm not sure how big the university's hard drives are. So I haven't put one up on my website yet because I just wasn't sure if there was room for one. Okay, probably is, but maybe I'll just do that. Maybe I'll just put a couple hundred megabytes of text up on my website and hope that the university has enough hard drive space to hold it. Okay, all right. So one compute bound program, that's all I need. Yeah, and then I'll show you these little scripts help make it easier to use it for testing purposes. And then a bunch of different I/O processes to exercise different parts of the I/O, downloading output to the console window and exercising your hard drive. Okay, sorry. So we've got this ability to run compute bound programs and I/O bound programs. Now let's see how we can use them to like do little experiments. Okay, so they open a console window. Okay, now remember I showed you this program the other day. If you just run it, there's the program. Well, first of all, I'll tell you. Okay, it tells you that you need to give it a command line argument. You need to tell it how many seconds to run. So I'm going to tell it to run 10 seconds. Then it runs for 10 seconds, and it tells you what its process ID number is, what the affinity mask is. That's what CPUs it's allowed to use, which CPU it's currently running on. You can see that as it was running, it kept getting moved from CPU to CPU. Now, right away, that's something we can relate to this picture. What that meant is that it was put on a CPU in the run state, and then its timer interrupt fired. So then it got moved to the ready state. Now, when it was just turned to run again, it was put back on a different CPU because I have multiple CPUs. Now, it does not transition from one CPU to another while it's in the running state. Windows would never do that. Okay, if you're in the running state, you're running on a particular CPU. What we're seeing here when it goes from CPU 4 to 3 to 10 to 2 to 4 to 3, we're really seeing that it went from the running state, its timer interrupt fired, it ran out of its time slice, got blocked. I'm sorry, got put back into ready because it's a CPU bound process. It's never blocked. It went from running to ready. Then when it got scheduled again, it just got scheduled on a different CPU. Okay, so it got scheduled on a different CPU, ran on that CPU for a little while. Then, yeah, and then maybe since it was on CPU here, sometimes it would stay on this particular CPU for a long period of time. If it was on a CPU for a long period of time, that probably meant it went back and forth from running to ready to running to ready to running to ready, always running on the same CPU. Then at some point, it went from running to ready back to running on a different CPU. Okay, so if you see it running on one CPU for a long time, there probably was several transitions from ready to running because you only stay in the running slot for about 50 milliseconds. I think Windows keeps you running for only 50 milliseconds. And these transitions are not 50 milliseconds. They're a little bit longer than that. Okay. So, but that's how it goes from one processor to another. This program is running by default on all 12 of my cores. Okay. Now, if I go back and run that for a real long time, I'm going to run it for a few thousand, like 1,000 seconds. Okay. Now I can bring up Task Manager and I can change the affinity of it. This is what we were doing the other day, but I didn't have it set quite right. See, the affinity mask that's 2 to the 12. 4095 is 2 to the 12. That's all possible CPUs. Now, remember, the CPU mask is a bit mask. If I right click here and set affinity, see, all the bits in a 12-bit word are set to 1. So that's this number here. For example, that's the number 3. If I click OK, see, the affinity mask is 3, and I'm running on processes 0 and 1. And if I go over here now, if I set affinity mask, like here's bit 0, okay, that's a 1. Here's bit 3. So that's 1's place, 2's place, 4's place, 8's place. That's the 8's place, the 1's place, that's the number 9. So see, the affinity mask is 9, and I'm running on processors 0 and 3. You can kind of see that I'm bouncing between processes 0 and 3. So the affinity mask is a bit mask, though it's displayed here in decimal. It's displayed here in decimal, but when you manipulate it over here, Windows shows it to you kind of as bits. You know, it shows you little check boxes, and you can just, what number is that in that's a binary number, 100100001. And okay, that number in decimal was 137. And I'm running on processes 0, 3, and 7. You can kind of see this. I don't know, actually, does Zoom show you this window scrolling, or is Zoom doing something weird like trying to stop it?
It's scrolling.
Okay, good. So Zoom is actually showing you it's scrolling. Yeah, and you can see that it was going between CPUs 3, 7, and 0. So, and 3, 7, and 0, I don't have it over here, I've lost it. But those were the 3 bits I set. So this number represented 3 bits. So this was 3 bits in the affinity mask, and those were processes 0, 3, and 7. And my program bounced between processors 0, 3, and 7. Okay, until it had accumulated enough CPU time. When it accumulated enough CPU time, it quit it. Okay, now CPU time is different than wall clock time. So now we want to talk about these, well, actually, okay, now let me show you I was running one process on many CPUs. Okay, what's more interesting is to run multiple processes on one CPU. Okay, what I was just doing was, like, think about my picture here. What I was just doing was I had one process, but over here I had multiple CPUs. So I had multiple CPUs running this one process. So sometimes CPU 0 would be running this process, and sometimes CPU 1 would be running this process. Okay, the process just transitioned between this running and ready state, but when it was running, it would run on whichever processor this operating system put it. Now, this program never really spent any time in the ready state because the computer, oh, like here, let's do another experiment. Run for 2 seconds. Okay. Now that took okay. Now I'm going to time. I'm going to time this. I want to run that program for 2 seconds and I want to time it. Time this times how long something takes. Well, if I'm going to run this program, compute program for 2 seconds, it should take 2 seconds to run. Notice that it took a tiny bit more than 2 seconds to run. The elapsed time, the amount of time it took from the time I started the program till the time it ended was just a hair's bit more than 2 seconds. Well, that extra time accounts for that has to kind of transition between running and ready. It spends a tiny bit of time in the ready state. But since there's lots of CPUs and they're not very busy, every time this guy transitioned from running to ready, there was a CPU ready to put him back running again. So he spent very little time in the ready state, but you can see a tiny little bit amount of time was spent in the ready state. Okay. And it was moving from processor to processor. So it took a little bit of time to move him from running to ready, then move him from ready to some other processor and run him on this processor. Then he would move from running to ready. And then when he was running, he'd run on some other processor. So he ran on processor 4, then 6, then 1, then 5, then 9, then 4, then 0, then 2. So he bounced around. So his wall clock time was a tiny bit more than the CPU time. Okay. Now, if I run like a 1 second job, it took a tiny bit more than 1 second to run that, but see, it bounced up a bunch of CPUs. Okay. All right. Now, what's more interesting than running one process with multiple processors is to run multiple processes on one processor. What I really want to do is run multiple processes on one processor and have the processor shared between the two processes, because then I'll see the wall clock time change. If this is running for 1 second of CPU time and this is running for 1 second of CPU time, and they're running on this CPU, it's going to take 2 seconds to run both of them. The CPU will bounce between them, but it'll take 2 seconds to give this guy 1 second of CPU time and this 1 second of CPU time. So let's do an experiment to show that that's exactly how Windows works. That if you put two processes on one CPU, it'll take more wall clock time to do that. It'll take the sum of the wall clock time will be the sum of their CPU times. Okay. Now, the way I run them on one processor is to set their affinity. So I wrote a batch script to do that for us. Now, we've been setting the affinity by going over here to the task manager and right clicking and say set affinity, but that's real time consuming. We want a more efficient way to set the affinity. So Windows gives you a more efficient way to set the affinity. This little script here, what it does, I'll show you, I'll run it and then explain what it does. So it's compute programs with affinity. Okay, so okay, you give it an affinity mask as a parameter, like the affinity mask 1. That means run on CPU 1. Then say run a 4-second job and another 4-second program. So run 2 copies of compute program. That's parameter. Parameter 1 is the affinity mask. See, there's this symbol here. This is shell scripting. This is the input variable to this program. That's the command line argument. Think of this as a function that takes in parameters. It's taking in, this function is taking in parameters 1, 4, and 4. The first parameter is called %1. In shell scripts, the first parameter is called %1. That's the affinity mask. Here's the way you use the affinity mask in software. You set the affinity and then run this program. Then what I have to do is I have to set the affinity, run CMD, and tell CMD to run time this, that's timing this program that runs for that many seconds. That's the second command line argument. Okay, so this is I'm programming in a shell script. So I'm saying start with Affinity, CMD. CMD's job is to run time this of that program with that parameter. And then it's going to do that with the other parameters, the other command line parameters. It's going to try to launch 1, 2, 3, 4, 5 processes, but I only gave it 2 command line arguments. Okay, so 3 of these processes just launch and die right away. It'll actually launch 5 processes, but these 3, since they don't have arguments, they'll just essentially in a millisecond, they'll launch and die right away because they don't have arguments. Okay. Now, what that's going to do is it's going to run 2 instances of compute on 1 CPU. Now, 4-second job and 4-second job on 1 CPU should take 8 seconds. Okay. So now each program will get, okay, what? There's one of the ones that died. There's one of the ones that died. And there's one of the ones that died. There's the 2 that are running. Notice that each one got 4 seconds of CPU time, but it took each of them about a little over 8 seconds to run. And the whole thing took, oh yeah, okay. I didn't time the whole thing. I'm only timing these 2 individual ones. So you see that each one of them took about 8 seconds to run because they're sharing 1 CPU. So each one got 4 seconds of CPU time, but it took them 8 seconds of wall clock time. Okay, now do that experiment again, but give it 2 CPUs. That would be the Affinity Mask 3. But if it's got 2 CPUs and I'm running 2 4-second jobs, they don't have any problem. They should be able to complete in 4 seconds. Okay, there's the one that was dead. There's the one that's dead. There's the one that's dead. And notice that each of them ran now in 4 seconds. Now, notice that they bounced between the 2 CPUs. The operating system did not put one on CPU 0 and one on CPU 1. It literally bounced them back and forth between the CPUs. But since if CPU 0 was running one process, CPU 1 was free. And if CPU 1 was running one process, CPU 0 was free. So always one of the CPUs was in use, and it took just barely over 4 seconds to run each one. Okay. Now, what if I do 2 CPUs and 3 processes? What if I do that command, but with a 4th one? Now there's 12 seconds worth of compute time to do, but only 2 CPUs to do it. Okay. Okay. So let's see what happens. So I'm going to run 3 processes, and I'm running 3 processes with a total of 12 CPU time, 12 seconds of CPU time when I have 2 CPUs. So I probably should end up doing 6 seconds of CPU time on each one. So it should end up taking about 6 seconds. Okay, there's one of the ones that didn't have anything to do. There's the other one didn't have anything to do. See, took 6 seconds, 6 seconds, 6 seconds. And the 3 processes each got 4 seconds. See, they got 4 seconds of work time. Each one got 4 seconds on the CPU, but the CPU had to rotate them around between the 2. The operating system had to rotate them between the 2 CPUs. There was 12 seconds of work to do. It took 6 seconds to do 12 seconds of work on 2 CPUs. On the other hand, if I did that same, okay, let me close these. I'm accumulating too many of these around. Notice that you with the right little setup, you can do experiments and see that the operating system is doing exactly what the textbook and the theory tells us it would do. Okay, so we're just seeing that it's doing exactly what the theory tells us it should do. Okay, now let's do the last one. Let's give it 3 CPUs. Okay, to give it 3 CPUs, if I use it CPU 0, 1, and 2, that's the number 7. The number 7 are the CPUs 0, 1, and 2. So that's the ones, that's 1's place, 2's place, and 4's place added together. 4, 5, 6, 7. Okay, so this should take 4 seconds. There's 12 seconds of computing to do, but there's 3 CPUs to do the computing. There's the one that wasn't used, and there's another one that wasn't used. Okay, it took 4 seconds. See, each one was done in just a little. Now the overhead is because they actually are bouncing around. Notice that the operating system didn't do something like, oh, let's put one process on CPU 0, let's put one process on CPU 2, and let's put one on CPU 3. It bounced them around, but there was always a free CPU. So any given process kept moving from 2 to 0 to 1 to 0. See here, it stayed on 0 for a while, and then it moved over to 1, whereas the other one, I mean, if you actually watch, you'll see that none of them could be on the same CPU at a time. So this one started off on 2. This one started, oh, actually, it did look like they started off on the same CPU. Yeah, this one started off on 2. This one says 2. See, well, that's because this is not, there are transitions that we don't see here. We only see the change from one CPU to another every, I'm sampling what's going on. If you look at the code, this is just a sample. This is not, if you think in terms of this picture, I'm not updating the output every time you move from here to here or from here to here, because that happens every 50 milliseconds. If I can't update it that often. So I'm updating this screen every once in a while. So every once in a while I say you're running on a CPU. So the screen over here is really just a random sample of the running. So it turns out that by coincidence, at the beginning, it just appeared like it seemed that these two processes were running on the same CPU. But in fact, they never can both be running on the same CPU at the same time. What about the other one? Yeah, initially, it looked like they all started on CPU 2, but that's just because that's just the quirk of the random sampling. Okay? We know that they moved around a lot, but this is not saying that this line and this line is not a transition from here to here, back to here. There could have been 1,000 transition between here and here in just this between here to here, because this is a fairly long period of time. See, from here to here was 4,000 milliseconds. This is sampling. This is sampling taking place on the order of like a few hundred not thousands of. There's from each line to the next line is a few hundred milliseconds. Okay, so there's a few hundred milliseconds from here to here, but your running time is only about on the order of about 50 milliseconds. So to go from here to here, the program could have been transitioning from here to here 3 or 4 times. The program could have transitioned from here to here 3 or 4 times, but we only see one transition here. So this is just a sampling of what's going on. If you look at the code, what the code does, to run on the CPU, it does a big for loop of cosines. Cosine's a kind of complicated floating point operation. I have this thing called compute counter, which you can set. Right now, it's set for 1 million calls to cosine. So this is 1, 2, 3, 1, 2, 3. So it does 1 million calls to cosine. Then it does the sample. It asks, what's the affinity mask? What processor number am I on? And it prints out the result. Then it goes back and does another million cosines. Okay, a million cosines takes, that's more, I don't think you can do a million cosines in one time slice. So I think that's several trips between running and ready and running and ready to do 1 million cosine operations. Okay, so this keeps you bound to the CPU. Okay, computing the cosine of these integers from 0 up to here. Okay, so that just exercises the CPU, make the CPU do something, and then ask the operating system, what's my current affinity mask? What processor am I currently on? Print the results, then go back and just do that calculation. In the middle of this loop is usually when it's going to be, when it goes from running to ready, it's usually going to be in the middle of that loop. Now, when it actually does this little IO operation, notice that it will do one little IO operation to print the screen. So this program, this compute bound program is not 100% compute bound. Every once in a while, it does one IO operation to print a line to the screen. Okay, so it runs for a long period of time, does one IO operation, so it'll get blocked for a tiny bit of time here. So that's part of the overhead that we see. When we see that these programs take a little bit more than their 4 seconds, they had to do a little tiny bit of I/O. So there's a little bit of I/O time in this wall clock time. There's a little bit of I/O time, and then there's the amount of time it takes to do the transitioning between these states. Okay, so you'll never have 4 seconds of compute time taking exactly 4 seconds of wall clock time. 4 seconds of compute time is going to take a little tiny bit more. Actually, you notice it's like 4 1/3 seconds. So it adds up. The extra overhead does add up a little bit. Okay. All right. So you can play around with these scripts and you can do different experiments. Okay. This is the compute bound program. This script here runs multiple instances of them, timing them. Okay. So if you want to run 5 of these, you could try to double click this guy. You'd have to open 5 consoles or type real fast to run 5 times. So I wrote a batch script that will let you run 5 of these. Okay, so the batch script is called compute programs. There's the batch script. Okay, if you give it run for this long, this long, this long, that runs 4 programs, three 3-second ones and a 4-second one. There they are. Well, actually, and then there's the 4-second one. There's one of the 3-second ones. There's one of the 3-second ones, and there's one of the 3-second ones. And then there's this one here. Okay. See, it launched 4 of them. It launched a 3-second one, a 3-second one. See, it launched a 3-second one, a 3-second one, a 3-second one, and a 4-second one. Okay. Then it launched a 5th one with no parameter, and that one just died. Okay. The script is kind of dumb. The script always tries to launch 5. It should actually ask how many command line arguments there are and only try to launch as many as there are. But I didn't feel like writing a more complicated script. So I just pretend that there are 5 parameters. I could have wrote an if statement in here that said, or a while loop that loops on the number of parameters. Actually, I probably should give it the while loop. Okay, I could turn this into a little while loop that whiles on the number of command line arguments. So I would only launch as many as there are command line arguments. That's writing code in shell script. Okay, so I can write if statements and while loops in shell script if I want. Okay, so I've got this one will launch a bunch of them. Okay, now close all these. Accumulate too many windows. The windows stay up so you can read what's in them. So the windows, you don't want them to close. You want them to stay up so you could see what was in them. Okay, that's the compute program that runs multiple of them. This one is this one where you can set the affinity. Okay, so there's not much difference between these. One of them just lets you set the affinity. Okay, this one runs them on the default affinity, and this one, each one is given the first command line argument is the affinity mask, and so they're all run with the same affinity mask. Okay, so it starts each one with the affinity mask. So it runs CMD with that affinity mask, then CMD calls time this with the program. Okay, here you just start CMD telling time and you start CMD. Start says essentially launch something in a separate window. So by saying start, it launches it in a separate window. If I got rid of the start, this CMD would launch in the same window, then it would wait for it to be done, then it would run this one. This says launch in a separate window, and then the CMD in its window should run time this, and it should time this program. Then this script launches another CMD in a separate window, and that CMD runs time this on a compute program with a different parameter. Okay, and this one does the same thing, but just before starting the CMD, this one sets the affinity mask for the CMD. So it starts a CMD with that affinity mask, and then that CMD is running within that affinity mask, and they're all going to be running on the same affinity mask. But then the time this is running with that affinity mask. The CMD is given that affinity mask, so it passes it on to time this, and time this passes it on to compute program. And then this is the parameter for how long it should run. Okay. So you can run them with affinity set or not with affinity set. Okay. And then notice that when I do it this way, I can't time the whole thing. Okay, I'm timing each individual one. So if I say do computes, okay, and I say like a 4-second job and a 5-second job and a 6-second job, okay, each one of them gets timed, but I don't know how long the whole thing took. I don't actually time the whole thing. Okay. Do it again. See, do this. Okay. See this one. Let's see what happened. What am I doing? Oh, I didn't mean to time. I did time this. I didn't mean to. What am I doing here? Oh, there's a little bug in this script. I just noticed that. I forgot the %1 here. I didn't even, I just realized there's a little bug. This is the one that doesn't use the affinity mask. So that should start with %1. That's why I was all of a sudden I was real confused because I said run 3, but it only ran 2. And that's because it was dropping the first command line argument. So I'd forgotten somehow I had somehow deleted the first command line argument from this list of command line arguments. Okay. All right. So, whoops. Okay. Open a command window here. Okay. Oh, I'm switching between this program and this. When you run this program, I'm running the wrong batch script here. Okay. When you run this program with this batch script, you time the individual copies of this one, but not the whole thing. So I want to look at not do compute. That's the next one I want. But right now I want to look at compute programs. Okay. See, it times each one of these, but does not time the whole thing. Okay. It just times each one of them. But so if you run this one is compute programs. Okay. If I say run a 4, 5, and a 6-second job, it tells me how long each one took. See, one took 5 seconds, one took 6 seconds, and one took 4 seconds. But I don't know how long the whole thing took. It's because it's a little bit hard to time the whole thing. So I wrote another program that lets you time the whole thing. That had to be done in a separate program. So here's how that works. This program here, do compute, is like your homework assignment that you just turned in. It runs a for loop that uses create process to launch it launches this guy. So do compute does this one over and over again. That way I can time this program and see how long the total time is of these. Okay, it's hard to time a shell script. So this program does what this shell script does. This shell script launched a bunch of these. This program launches a bunch of these, but I can time that program. So now I can time the whole bundle, but then I can't time the individual programs. Okay, so when you use this shell script, it runs, or you use this program. Okay, if you like do compute, if you call do compute, it runs. This says run a 4, a 5, and a 6-second job. See, but it doesn't time anything. See, when the programs are done, they just disappear. See, so that runs a 4 and a 5-second job. The 4 or 5-second jobs pop up, and then they die. Okay, this runs 3 1-second jobs. They pop up, and they die. Okay, it doesn't, no timing. If you want timing, then this shell script does the timing. So do, well, now 1-second job, 1-second job, 1-second job. The 3 seconds job popped up, and it took just over 1 second to run 3 1-second jobs. Okay, like run a 2-second job, a 3-second job, and a 4-second job. Notice it took 4 seconds to run a 2, 3, and a 4-second job. You know, the amount of time it takes. See, this is now the total amount of time it took to run those 3. Now, since they're on multiple CPUs, the 2-second job finishes in 2, the 3 seconds finishes in 3, this one finishes in 4, and this one's telling me how long the longest running of them took. Okay. Now, what if I want to do that with the affinity set? For example, now 1, 1, 1, 1, 4 1-second jobs takes 1 second. Do it with affinity, and now I can do it with affinity. Set the affinity to 1, so there's only 1 CPU. Then run a 1, 1, 1, 1. Run 4 1-second jobs with 1 CPU. It took 4.5 seconds to run. See, now the timing information is in this window. Because of the way these scripts work, I ran it in this window. The timing is done in this window. So 4 1-second jobs took 4.5 seconds. The extra half second is the overhead it took to do the launching of these and the time switching between them. So now, what would it take? See, what if I ran 4 1-second jobs on 2 CPUs? So here's 2 CPUs, 4 1-second jobs on 2 CPUs. The total runtime should be 2 seconds. See? A little over 2 seconds to run 4 1-second jobs on 2 CPUs. So you can see here, what I ran was 4 1-second jobs. So I'm timing this guy with 4 1-second jobs, and it took a little over 2 seconds. This is the guy that was launched with the Affinity Mask. So this window set the Affinity Mask and launched this window that launched that program with those parameters. This ran 4 1-second jobs with the Affinity set to 3, and it took 2 seconds. Okay, so notice that none of these are long programs. These are 1 and 2 line shell scripts running simple programs, but they give you a sense of how to play with this is how operating systems people experiment with operating systems. This is how they test algorithms and show you what an operating system is doing. Writing combinations of C programs and shell scripts, we can see that the operating system is doing what we claim it does. Okay, yeah. If in the case over here, if I want 4 1-second jobs on 2 CPUs, it's going to take more than 4 seconds because they're only sharing the 2 CPUs. Okay, let's do one more. Let's see. 3 CPUs would be 7. That's 3 CPUs, and then run. Let's see. 3, 3, 3, 3. Okay, there's 1, 2, 3, 4, 5 3-second jobs. 5 3-second jobs on 3 CPUs. See, 5 3-second jobs is 15 seconds worth of work, but there's only 3 CPUs, so it should take 5 seconds to do this 3 seconds worth of work on each of for each of 5 processes. Let them run, they die, and I find out, yeah, 5.5 seconds to do 15 seconds worth of work on 3 CPUs. Okay, so see, I was 1, 2, 3, 4, 5, 5 3-second jobs, and I know that I launched that on 3 CPUs. That was over here. I launched it on 3 CPUs. That 3 was the 3 was the I'm sorry. That was the 3 CPUs. That launched this command line, and this command line launched that command line, and then this one timed it. This one timed the 5 processes, each running for 3 seconds, but this one's restricted to 3 CPUs, so it took 5 seconds. Okay, so the operating system is doing exactly what the theory says it should do. It's behaving exactly what these pictures say should happen. You know, you can only run one CPU, a CPU can only run one process at a time. Okay, and if you have a certain amount of work that needs to be done and you share it between these CPUs, you can figure out arithmetically how much time it's going to take. 15 seconds worth of work to be done by 3 workers is going to take 5 seconds per worker. So it took a total of 5 seconds. Okay, all right. Now, what's interesting is if you throw in this IO bound, that won't affect the CPU bounds. Now, one of the things to do is to say that the IO bound process, if you throw one of these IO bound processes in, most of the work is done not by the CPU, but by say the hard drive, and it won't really have any effect on the CPU bound processes. So let's see if we can do one experiment like that. Okay, so let me try to set up one experiment like that, mixing IO with CPU. Okay. Now, let's see. The best way to do that, okay, open a window and create a bunch of CPU. Well, let's see. Let me get the text file. So let me just download the text file first. Okay, see, there's the text file. So there's a kind of semi-big text file. Okay, a kind of 6 megabytes of text. This file here will take that file and turn it into a 1 gigabyte file. So that'll do a lot of IO on my hard drive. So that'll make my hard drive really work hard. So what I want to do over here is run an IO. I just run by double clicking on it. There's no sense of affinity to this because the work is really being done by the hard drive. So this thing doesn't need a sense of affinity because in terms of this picture over here, the work is being done mostly by the hard drive. The hard drive is to be copying data from the hard drive to memory, from the hard drive to memory, and back and forth. So that the work is being done between the memory and the hard drive, and the CPU isn't really involved. In modern computers, the CPU does not do the IO. The IO is actually done by the IO devices. Okay, so there is no sense of setting affinity for an IO process. I can set the affinity, but it doesn't really mean anything. Okay? It would just be this batch script would run. What little time is spent running this batch script would be on one CPU, but the vast majority of work would be being done by the hard drive. So this, if I start this guy up, it'll work for quite a while. Then at the same time, I can launch in here a compute bound process. Now, so let's see. Let's do something that will take a fair amount of time. Do computes. I'll do it without the affinity. So do computes and run, say, a 30-second job, a 30-second job, a 30-second job. Okay, now that's 5 30-second jobs, but I'm not setting the affinity, so that'll keep 5 cores busy for 30 seconds. And this will keep the hard drive ready. What we should see is that these things take exactly 30 seconds to complete. they shouldn't really be affected by all the work that's being done by this one here. Okay, so start that one. Okay, start this one. Now this one keeps doubling the file. Notice that this one, at first it copied it from 6 megabytes to 12 megabytes, from 12 megabytes to 24 megabytes, from 24 megabytes to 48 megabytes, from 48 megabytes to 96 megabytes, from 96. Now it's going to take longer and longer because it's actually starting to do more and more I/O work. So right now the hard drive's copying bigger and bigger files. Okay. Now my computer should be both. Oh, and notice that this guy finished in just over 30 seconds. Yeah, the I/O is still working, and these guys all finished the CPU, the compute bound ones all finished in 30 seconds. Okay, so all the compute bound ones finished in 30 seconds. Do you see? There was a little bit of work on the disk drive, not much. There's the notice that, in fact, that multiple gigabytes of activity on the disk drive, modern disk drives, that didn't even really stress the hard drive very much. That's one thing about this, is it's actually hard to stress the modern hard drives. So that really didn't stress the modern hard drive very much, but it did create this. See, this file is now 1.5 gigabytes. So it did a lot of I/O. This file grew to 1.5 gigabytes, but it didn't affect it didn't affect my. See, it took these 5 processes ran in just over 30 seconds. The I/O operation didn't impinge on them at all. Okay, and that's kind of what we would expect from the theory, is that the I/O operations are taking place on the hard drive, not the CPU. So with a modern computer, all the I/O is done by the hard drive. Now, unfortunately, the kind of hole in this experiment was I hardly really didn't exercise the hard drive that much. Okay, I'd have to write. I probably would have to write, if I want to really exercise the hard drive and push as much data through the hard drive as possible. I can't really do it with a shell script. Okay, I have to write right now what I'm doing. If you look at this shell script, the one that makes the huge file. No, let's see, where is it? I'm asking Windows to do the I/O operations. I'm asking Windows, take this big file and append it to itself. The trouble is Windows is notoriously not very good at doing I/O by itself. The Windows operating system takes a really not very, it doesn't try very hard to do I/O in a fast way. So essentially I'm asking the Explorer to make the file copying, and Explorer is notoriously slow. It does not push data through the hard drive as quickly as possible. If I wanted to do this really pushing data through the hard drive as fast as possible, I have to write my own code to copy that file to do the appending. Because then I can use techniques that the Explorer doesn't use to push more data through the hard drive. I can do something called memory map files and a few other things. So unfortunately, I don't get a good experiment here, because even though I'm keeping the hard drive busy, I'm not keeping it very busy, only keeping it slightly busy. It takes real effort to get the hard drive to saturate, to get as much data going through it as possible. Okay, we run that again. Oh no, here. Delete that. Delete that file. Download it again. Okay. Now run the script that turn it from a 6 megabyte file into 1.5 gigabyte file. So run this script here. Okay, now it's working. And you won't see the hard drive get very busy. See the activity time down here. The hard drive's even though this is, you would think that the operating system would say, let me do this as quickly as possible. I've got this work to do. I should maximize the throughput through the hard drive. No, the operating system, Windows is not written that way. It does not try very hard to do fast IO operations. I'm not sure why. So it's not trying at all to maximize the throughput through the hard drive. So see, it's barely using the hard drive. Okay. So that makes my experiment a little bit shaky. Yeah, even if I did push data through the hard drive as much as possible, it still wouldn't affect my CPU bound processes because I would be using the IO system more efficiently. Windows just doesn't use it very efficiently in the Explorer like this. I mean, there are other versions like Microsoft's database server and Microsoft's web servers sure know how to use the hard drive as effectively as possible. Their database server really, 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 really knows how to use the hard drive as effectively as possible. But the Windows desktop like this doesn't. See, it doesn't. Oh, what happened there? Oh, I must have cleared. Somehow something funny happened when I moved the window around. My windows went away for some reason. Okay. But Windows didn't try very hard to use the I. It's still busy. It's taking that. There, it finally finished. I think it finally finished that hard drive, that copying. Yeah, it's finally done. Okay. Yeah, you can see the history. It ended around about here. It did not stress the hard drive very much. The hard drive didn't try to do that I/O operation anywhere near as fast as it could have done it. Actually, you might ask, how fast could I build that file? See, that's a 1.5 gigabyte file. I started with a 6 megabyte file and I built it up to 1.5 gigabytes, and it took about a minute to do it. You might ask, how fast could you do it? How fast could I have copied that file from, say, from 6 megabytes to 1.5 gigabytes? The answer is about 10 seconds, probably less than that even. If I wrote a program to do it myself and I did all the tricks it took to get the hard drive to work as quickly as possible, I'm sure I could get that file from 6 megabytes to 1.5 gigabytes in less than 5 seconds, probably less than, maybe even less than a second. The hard drives are super fast. Modern hard drives, they can push data at unbelievable rates, but the Windows operating system, at least the Explorer, doesn't even try to. The Explorer doesn't even try to use the hard drive as fast as it could. Okay, so you have to write code to make it. If I really wanted to stress the hard drive as fast as possible, I have to write code. Okay, and that's actually the next set of programs. We run out of time, but the next set of programs starts showing you how to do that. Okay, this set of Windows system calls. Okay, we'll do this on. We'll do these on Wednesday. We're going to do this buffering and system calls, this folder here. This folder here shows you how to start writing fast IO code. Okay, it starts hinting at what's the way to write, because what this thing does is it creates the large text file. Oh, it's going to, well, I'm sorry, it downloads the large text file. See, it downloads that large text file, and then it starts copying it. And it does it in a bunch of different ways. Okay, a slow way, a slightly faster way, a slightly faster way, and it shows you that how fast you can copy data depends a lot on how you write your C code. You can write dumb C code that takes forever to copy data. Then you can write smarter C code that takes that's much, much faster, and that has to do with system calls. We'll see that what you want to do is you want to write C code that minimizes the number of system calls. Every IO operation is a system call. Every time you want something to happen on the hard drive, you have to ask the operating system to do it. System calls are very slow. If you make a lot of system calls, your program's real slow. One of the ways, not the only way, but one of the ways to do fast IO is to make a minimum number of system calls. Now that means you have to make your system calls make the most data. Instead of making lots of system calls that move a little bit of data, you make a few system calls that move a lot of data. So we'll see. That's what we're going to do on Wednesday. But a lot of programmers don't know this. So they accidentally write programs that make huge numbers of system calls that each move little bits of data, and they wonder why their programs are so slow. When they're supposed to write their code using buffers, the issue here is buffering. You're supposed to write code that makes a small number of system calls, but uses very large buffers, as opposed to making a lot of system calls using a small buffer. So we'll see that makes a huge difference in the performance of your program. And the issue is all about system calls. How many times do you do this? How many times do you transition? How many times do you do a mode switch from user mode to kernel mode back to user mode? Switching from user mode to kernel mode back to user mode is slow as it can be. It's one of the slowest things the CPU does because it's a very complex operation. It involves a lot of the security of the CPU. Switching from user to kernel is slow, so you want to avoid it. Okay, so that's where we'll pick up on Wednesday. We'll go to this folder on Windows system calls, and we'll see that it is part of the secret of writing fast I/O because you want to write code that minimizes system calls. Okay, all right. So that's where we'll pick up on Wednesday. Anybody got any last question? Uh, try these experiments. Try these experiments. They're pretty interesting. If you really want to start getting a sense of how your computer works, these experiments are giving you a sense of what's really going on in the operating system. This is the kind of performance issue that programmers hopefully understand how their CPU really runs their code. Not just write their code and it's correct, but then you start asking, well, but okay, how does the CPU really, really run my code? What are the performance implications of the way I wrote my program? Any last question? So please play around with these, experiment with these experiments. Yeah, they're a good way for you to get a sense of how things work. And you're going to have a programming assignment that's very much along this line. The next programming assignment is going to be very much similar to what these experiments do. Okay, so I'll stop sharing and we'll meet again on Wednesday. And like I say, on Wednesday we'll start playing with the really playing with the system calls. Okay, see you on Wednesday. Bye.